This research paper explores the use of mathematical modeling and simulation techniques to design and fabricate 3D printed porous tissue scaffolds. The primary focus is on optimizing scaffold design for chondrocyte cell growth, which is crucial for cartilage regeneration. The researchers employed two key mathematical modeling techniques, the finite element method and the Monte Carlo method. FEIN helps analyze the structural properties of the scaffold, while the Monte Carlo method simulates the random distribution of cells and nutrients within the scaffold, aiding in design optimization. Computational fluid dynamics, CFD, plays a crucial role in understanding the flow of blood and nutrients through the scaffold. ANSYS Fluent software is used to simulate this flow, considering the properties of blood and the scaffold's porous structure. The simulation helps analyze the velocity profiles, pressure distribution, and frictional losses within the scaffold. The designed scaffold models are then fabricated using 3D printing technology. Chitosan and its composites are used as materials for printing. Scanning electron microscopy, SEM, is used to analyze the scaffold's morphology and confirm the desired pore structure. Human mesenchymal stem cells, HMSCs, are cultured on the printed scaffolds to evaluate cell growth and differentiation, validating the scaffold's suitability for tissue engineering applications. The simulation results from both the Monte Carlo method and CFD provide valuable insights into the scaffold's properties. The Monte Carlo simulation shows that the scaffold has a desired porosity level and cell distribution. The CFD simulation reveals the blood flow dynamics within the scaffold, highlighting the velocity profile and frictional losses. The 3D printed scaffolds successfully replicate the designed porous structure, and cell culture studies confirm that chondrocytes grow and differentiate well on these scaffolds. This research demonstrates the effectiveness of mathematical modeling and simulation in designing and optimizing 3D printed tissue scaffolds. The study provides valuable insights into the relationship between scaffold design, blood flow dynamics, and cell growth, suggesting that Chitosan scaffolds are suitable for cartilage regeneration. The authors propose future research directions, including exploring different scaffold materials, refining modeling techniques, and conducting in vivo studies to further validate the scaffold's performance in real-world applications.